When we are dealing with combinations of our transformations, we're going to be maybe dealing with many of our different manipulations of the equations, but all at the same time. So let's just summarize from lesson 4 what we know about transformations. So we take our function y equals f of x, and we can manipulate the equation in 4 different ways. Okay, so we have y equals a times f of b, and I'm going to write here x minus c, just so that we can have c as a positive number, which is a little bit different than I explain it in lesson 4. And then we're going to be dealing with plus d. So there's sort of 2 things that are happening. So we have 2 things that are happening outside the function. So these are things that are happening after the function has been performed. So we think of these as our outside of the function transformations. And these will always be acting on y. Our inside of the function transformations here will be happening on x. So those are things that would be in brackets attached to the x before the function has been performed. So something like an x minus 3 bracket, then you square the function. That would be an inside the function. So whatever your function is, if you think about your basic function, and we have 6, so let's review. We have our 6 basic functions, y equals x, y equals x squared, y equals x cubed, y equals the absolute value of x, y equals radical x, and finally y equals 1 over x. And so transformations take that same basic shape and move it around in some way. So let's summarize what these different letters mean. So if we give an example, here we have y equals 3 times the absolute value of, and I'm going to put a 2 here just so that we can see what these different numbers are doing. However, it's really, we'll talk about it in a minute, but it's really unlikely that you'll have a number for both a and b, and that only happens generally with trigonometric functions, which we'll address later in the course. So we have a, b, our c, and our d. Okay, so these are the different placements of the numbers that have been added into this function. Our base function here is y equals the absolute value of x. So if we're going to graph this thing, we know that it's going to have this basic shape, but that shape will have been manipulated in some ways. And remember that the transformations we're performing are always transformations on the base functions. So if you're doing a transformation of an absolute value function, your end result should still look like an absolute value function. You're just moving it around and possibly stretching it out, or compressing it and possibly flipping it around, but it should still have that same kind of pointy parabola look. Okay, so let's just remind ourselves what these different letters mean. So A is a vertical expansion or compression. And what we're actually doing when we're computing the A is we're multiplying the y values of our base function. So if you have like a point that's like 1 comma 2, that same point would be transformed to 1 comma 4 because you multiply the y value times 2. Okay, so we have expansions happen when the absolute value of a is greater than 1, which means the distance a is bigger than 1 or smaller than minus 1. And a compression is when the absolute value of a is between 0 and 1. So again, the number part without reference to the sign. Okay, it can be a vertical expansion or compression. Okay, it can also be and or a reflection in the x-axis or the y direction if a is negative. And I'm just going to remember this a less than 0 is a mathematician's way of saying negative because it's actually shorter than writing out the word negative. And one thing you will learn about mathematicians is that they don't like to write unnecessary characters. Okay, so B, I'm going to put a little star by B because B operates, because it's acting on X, it operates kind of backwards from how you would think it does. So A, expansion is when you have a big number, so that stretches it, and that makes sense. And compression is when it's a small number and it shrinks it. That kind of makes sense. B works the opposite way. So B is a horizontal compression whenever the absolute value of B is greater than 1. So B is bigger than 1 or smaller than -1. It actually compresses it. I like to think of this as it's speeding up the function and making it happen faster. It's also going to be an expansion if the absolute value of B is between 0 and 1. Okay, and it could also be or a reflection in the y-axis if B is negative. So that's the same way. If B is negative, you will be reflecting in the y-axis. Notice that B, and this is a big star, notice B is factored. Okay, so we can only really identify what our B is if we factor it out. It actually isn't going to prevent you from understanding what the B is, but it may help you to be able to then, if there's also a horizontal translation, it can help you actually identify the correct horizontal translation that you need to do. And it does, the reason for this has to do with the order that these things happen in. So one of the good things, expansions and compressions generally tend to be people's least favorite transformation to do. Usually though, for any of the functions, these 6 base functions we're talking about now, usually we won't have horizontal compressions or expansions. And there's certainly no need to have horizontal compressions or expansions in the same function as a vertical expansion or compression. There are going to be, when we get to trigonometry, these things are actually going to have a different result on the graph of our function. But essentially, for any of the functions that we use, we could rewrite a horizontal compression or expansion as a vertical expansion or compression. So we don't actually differentiate it that much. And we tend to write things as vertical expansions or compressions and not horizontal expansions or compressions. So you will rarely see a B that has a numerical value. You will often, however, see a B that is negative. So that negative, especially when we're talking about a radical. So for some of our base functions, putting a negative there isn't going to have any effect, like x squared or absolute value of x. For some of them, it's the same thing as putting a negative in front. But where you really need to be careful about that horizontal reflection is in our radical. Okay, y equals radical x is really the place where you need to be looking out for that horizontal reflection as opposed to a vertical reflection. And some functions, a vertical and a horizontal reflection, have pretty much the same effect. So we have our C, that's the number added or subtracted. So this is a translate x. Okay, so when you have f of x goes to f of x minus c. In this way, this goes right if c is positive and left if c is negative. Okay, so if you're subtracting a positive, you're going right. And if you're subtracting a negative or adding a positive, you're going left. And this again works like B, because it's acting on x, it works the opposite of the way you would think it would. Okay, so now we are going to our last one, which is translate y. Okay, and that is the number that we're adding or subtracting on the end, and this one works just how you think it would. So you have up if the number you're adding on the end is positive, and down if the number you're adding on the end is negative. Okay? So generally, what you're going to be doing, and the order you're going to be doing this in, is if you have your y equals a, f of b times x minus c plus d. First thing you need to do is you need to make sure that if you have a b, it's not that there's like a negative or any other number in here. B must be factored. So if it's not factored inside your function, you need to make it factored. Otherwise, your horizontal translation won't come out properly. Okay? We always deal with our reflections and our expansions or compressions first. Okay? And then we deal with our translations. Okay? So expansions, expand or compress and reflect before translating. And this has to do with mathematically how these changes affect the outputs of your function. But suffice it to say, I'm not going to explain exactly how, because that's going to depend a lot on the function. But generally, what would happen if you did it in the wrong order is that you would be, when you're expanding and compressing, we generally consider that to be around the origin. And if you've already moved something before you try to expand or compress, you have to do it without reference to where its original position was. So it works a lot more easily if you just do it when it's in its original position and you're multiplying x values, multiplying y values. Similarly, if you've moved, especially with that horizontal expansion or compression, you really want it to be in that base position, right where it is supposed to be around the origin, which is our 0, 0. Okay, so let's take a look at an actual function. Okay, so if we have y, just to see what would happen if we were to write it in words. So y equals 3, the absolute value of 1 minus x plus 4. Okay? So here we have, if we factor out this b, so we have to rewrite it, so this is negative 1 times x minus 1 plus 4, so we get our b. So this is our a, means we have a scale factor of a. This is our b, which is a reflection, and we have a horizontal translation and a vertical translation. So let's actually see how that graphs. Okay, so what I usually do is I will start with my base function right here. Okay, so this is my base function. Then I will do my expansion. So my a is 3, which means if I have a point here, say at 1, 1, that point with the same x value will be multiplied by 3. So that will actually go to 1, 3. That's my point on my new one. Similarly here, if I have negative 1, comma 1, multiply that number by 3, goes up to negative 1, comma 3. And you can see that for functions like lines and absolute values, this is really just changing our slope. So we've got now a, quote, slope of 3 for this absolute value. With curved functions, it doesn't work quite the same as slope, because you need to get to calculus to calculate slopes of curved functions. But here we've got, but with these straight line functions, you really can think of it as just changing the slope of that function. Okay, so now we have our b. We're going to do our reflection. It's okay if you do a first, then b. It's not going to necessarily help. But what I notice is if I try to reflect this over the y-axis, that's a horizontal reflection, it stays the same. So I don't actually have to do anything for that b, and I might as well just take it away. For c, I want to move, I usually do c and d together. When we're doing a translation, what we really want to do is take one of those points we can kind of latch onto. So for me here, this is the vertex. So now I have kind of a slope of 3 going up on either side. So now I'm going to take that. I want to move it 1 to the right and up 4. So up 1 to the right, up 1, 2, 3, put in an extra line, 4. So now my function is going to be going up at a slope of 3, and it just has that new starting point. So I know how to find the next points once I've done it. Okay. So for those of you who prefer, let's say we have a small f of x right here. So we're going to take a look at our f of x. So let's say we have an f of x that looks like this. Okay, just some random function. There's two different ways. Let's say we wanted to map this to, so if this is f of x, let's make this a 1. This is a 1, this is 2. Okay, we want to map f of x to f of 2x plus 2 minus 1. Okay, so notice that plus 2, I can't just add the 2 and the minus 1 because the 2 is inside the function, whereas the negative 1 is outside the function. I don't even know how I would take that 2 outside of the function because I don't know exactly what that function does. So, method 1 is to use what we understand about this function and to try to complete this, to try to graph our new function. So let's rewrite this. We have a b, so we need to factor out this is 2 times x plus 1. Okay, and then we're going to subtract 1. Okay, so it looks like we have a horizontal compression of 2 with a scale factor of 2. We're going to go a translation of 1 to the left and 1 down. So let's do our compression first. So when we have a 2, we have a scale factor that we're multiplying our x's by of 1 over b. Okay, so in this case it would be 1/2. So what we're going to do is every x value is going to go to the x value that is half. So this point here that was at x equals 2, it's going to keep the same y value, but be multiplied by 1/2. So 2 times 1/2 is 1. Here we've got a 1, so 1 times 1/2 is 1/2, but it's going to keep the same y value. So this is my new, this is after compression. That's after our horizontal compression. So now I'm going to do my translations. So I'm going to go 1 to the left. So this is at 1/2, so it's going to end up at negative 1/2. I'm going to use that full 1/2. And it's going to go 1 down. So it's actually that vertex point is going here. That's my horizontal, and then here is my vertical. And then it's going to be graphed in the same way. So it's going to go, this point was here. Every point is going to move in the same way. So it's going to go over 1, down 1. And then this point up here is going to go over 1, down 1. So I wind up with the same bit here, except now it's at negative 1, comma negative 1. So for those of you guys who like a nice formula, we can actually generalize what's happening to each point. So a point m, comma n will map to m, our x-coordinate will be m divided by b plus our c, if we're thinking of c as the positive number that's getting subtracted. And our n, our y-coordinate, is going to be a times n plus d. Okay, and see, we finagled it so we've got our c being positive. Just remember we're talking about for x minus c. Okay. So we have that negative in there. So just remember that that is the way it will still look like the opposite of what you think it ought to. So for that, we can actually just plug in the formula right down. So b, for this example, we have b equals 2, c equals, remember it's x minus c, so our c here is equal to negative 1, and our d is equal also to minus 1. And I will leave it as an exercise if you want to confirm that the points I've calculated are correct given our starting points. So again, just to look at one more specific example function, we have y equals 3 radical minus, let's see if we have a 1 minus x plus 3. So if I want to straighten out this function, this is 3 radical minus x minus 1 plus 3. So this is a vertical expansion by scale factor 3. And I usually would do a separate drawing with your expansions and compressions because they are the hardest one. I wouldn't try to do that while you're doing also trying to deal with translations or reflections. I would just do the expansion and then deal with the rest of it. So we have a vertical expansion by scale factor 3. Okay, reflection over y axis, that's that negative one. And then we have a translate 1 to the right, because now that we've factored it out, we actually have it going in the correct direction. And then this one right here is translate 3 up, because the one outside the function, we can see the one is inside the function, so that's going to affect us horizontally. The 3 is outside the function, it's going to affect us vertically. And so one thing you might notice is, hey, this looks a lot like that looks a lot like our vertex form of a parabola. And you are right that the vertex form of a parabola is really just the transformations on having the parabola written in a form that shows us what our transformations are. So we can think of A as a vertical scale factor, right? And that was something you guys did last year with parabolas. The H is our horizontal translation. So that's where we have moved the vertex to, and this is our vertical translation. And the reason that we do that around the vertex is that nice turning point that we can latch onto, so we can translate that point, and then we get the rest of the parabola for 3 because we know how it works.